Hello everyone. This is Gayatri Priya, Assistant Professor in the Department of EC of RMD Engineering College. In today's session, we are just going to discuss about the scaling. How this scaling make an impact in our CMOS technology. Right? Okay. First, let us get into the technology scaling. So actually, we are going for scaling because of three major reasons. The first one is I just want to increase the transistor density, right? So I want to increase the transistor density, and also I want to reduce the delay occurring because of the gate, and also to reduce the power consumption of that, right? So basically nowadays we are having two categories of technology generations. The first one is doubling of the transistor density. The next one is the gate delay is reduced by 30 percentage, and the power is reduced by 50 percentage of the things, right? How this scaling can be achieved? Right. Here we are having two different types of scaling. One is lateral scaling, the other one is vertical scaling. So everything it depends upon alpha, which is nothing but a constant field. Typically, for a 30% reduction, 1 by alpha is taken as zero point 0.7, right? So these are the generalized scaling variables utilized. For supply voltage, that is VDD, VDD by alpha. For gate length, it is L by alpha, gate width W by alpha, and similarly up to this substrate doping. Right? Here I have mentioned two types of scaling. First one is going to be constant field scaling. The other one is constant voltage scaling. So what's the mean by constant field scaling? In the sense, the electric field across the gate oxide will not be changed, even though the scaling is made. Right? That is called your constant field scaling. If the power supply remains constant, whatever the supply voltage we apply, that is going to remain constant, then that scaling is called constant voltage scale. Right? So, what happens because of this scaling? Okay, so that's what we are going to see in this scaling consequences. So, we have told that we are going to make use of 30 percentage of scaling. That is, alpha is taken as 1.43 and 1 by alpha is equal to zero point 0.7. So, if you are taking an area is nothing but width into length. Therefore, this is 1 by alpha, this is 1 by alpha. Put together, it is called 1 by alpha whole square. That would be equal to 0.49, right? So if you are going to calculate the transistor density, okay, that is unit area by WL, which is nothing but alpha square. So by doing so, the memory density can be scaled as what we have expected. Similarly, the scaling consequences for gate capacitance, drain current, and gate delay are being listed out. Right? Since we have taken the 30 percentage, okay, gate capacitance is nothing but W into L by T naught X, that is equal to zero point 0.7, and drain current we know the formula W by L into V square by T naught X, where T naught X is going to be the thickness of the oxide layer, that is also equal to zero point 0.7, and the gate delay is CV by I, or simply we can say this is the frequency of operations. And similarly, the consequences of scaling on power and power density is being listed out. Power will be nothing but CV square F, that is equal to 0.49, and the power density will be increased. When compared to the normal things here, once it is being scaled, the power density seems to be very faster with increase in the frequency. Right? So hope you have understood the concept of scaling and how the power and the other concepts are being impacted. Thanks a lot.